We were looking at photoelectric effect as part of all the various effects that occur as radiation passes through the patient, and we had looked at various aspects of photoelectrics. The last feature of photoelectrics was concerning the fact that the contrast media effect is based on photoelectric effects, and sometimes also called the photoelectric resonant absorption effect. On this slide, we're going to thought I'd back up a couple of slides and mention again this idea of the K-edge. As we get more and more into dual energy CT, for instance, you're going to be hearing a lot about K-edge effects, and it plays a very prominent role in radiology. So let's take another look at that. What you see plotted over here is the probability of photoelectric effects as a function of energy. And what it says is, as we had already seen, that photoelectric effects get less and less and less important. They get less and less probable, less and less occurring in the patient as energy goes up. And then at one particular energy, all of a sudden you have this extraordinary increase, just straight up. And in terms of its occurrence and in terms of what's going on inside the patient, that extraordinary increase occurs and is referred to as the K-edge. It occurs at the K-shell binding energy of that particular material. And here I've drawn it for iodine. Iodine has this K-edge at 33 keV. And this K-edge occurs right at that energy. And it's a resonant absorption effect, and it produces an extraordinary increase in absorption, which in practice means that which you could not see now becomes visible if it is infused with iodine. That's the case with a blood vessel, which prior to the iodine contrast could not be visualized, but after the contrast is very readily visible. Let's okay. As we said, that occurs for 33 keV. Every material has a K-shell binding energy, so therefore every material has a K-shell effect. Now, for this to actually be practical, you have to operate a little bit above 33. 33 is right at that edge, and what you want to do is you want to be at the peak rather than at the bottom. So for this to be invoked, for this to work, you have to operate a little bit higher than the 33. About 35 keV will bring you right up to the peak. Now, what's the rationale for using iodine? And in fact, don't we also use barium as a contrast media? The rationale is that our typical beams have energies that correspond to the K-shell energies. Remember our Bremsstrahlung distributions, that the effective energies was in the 30s? Well, iodine has a K-edge at 33. Barium has a K-edge at 37. So the trick in contrast media is to match the energies that you're working with to the contrast media K-shell binding energy. Okay, there are those edges, and I've superimposed on this plot the iodine edge, and notice that it is smack in the middle of our typical spectrums. You want to have the absorption occurring where the photons are, and the photons are in the 30s for typical X-ray beams. And here we're comparing the iodine with soft tissue. Soft tissue with a much lower atomic number is way down lower in photoelectric occurrences, and iodine, just because it has a high Z, is already higher than soft tissue, but then it's extraordinarily high, extra high, at the K-edge effect, as you can see over here, so that your net subject contrast is going to be a larger difference between the iodine absorption and the soft tissue absorption, and the blood vessels then just jump out. Their conspicuity, their visibility is so much more enhanced. So in summary, then we saw that this edge occurs at the binding energy, and in fact, it has to be a little bit higher than the binding energy. And at that edge, you have extraordinary absorption of the X-rays. You cannot have right at the binding energy, because if the energy was right at the binding energy, notice then that there would be zero available. If you look at the energy conservation little rule, if if the energy was exactly equal to the binding energy, well then there'd be zero energy available for kinetic energy, and then the electron could not move away. And if it cannot move away, well, nothing will happen. So again, just emphasizing, you have to work at a little bit higher than the exact energy at the K edge. There's a similarity to a soprano singing a particular note and shatters a wine glass. That also is a resonant absorption effect, but it's more it's an acoustic energy absorption. When the soprano hits a note, a tone, a frequency that matches the molecular vibrational frequencies of the molecules in a wine glass, then there's an extraordinary increase in an energy there. And that's acoustic, but it's a very similar to what's going on with X-rays with the photoelectric K-edge effect. Okay, let's look at mammography. What would be an ideal contrast media for mammography? Well, mammography is down by the 20s, right? The 20 kVs, and we don't have a good contrast media that has a K edge in the 20s, right? We have iodine, but that's at 33. But yet we still use iodine as a contrast media in mammography. And there we don't utilize the K-edge effect. We're just utilizing the fact that iodine, just by virtue of its higher atomic number, will have more absorption than the soft tissue found in the breast. So you still have a contrast between the iodine and the soft tissue because of that Z cubed over E cubed effect. Remember that relationship? Very important relationship, which says that as you go down in energy, there'll be an extraordinary increase just due to atomic number differences. So if you remember, that's the reason we went to low energies to begin with in mammography, to enhance the atomic number differences, to enhance the atomic numbers, the visibility of different atomic numbers in the breast, which are very, very similar. Okay, well, let's move on. Here's a typical board question. It says, find the optimal energy for an angio study. Okay, well, remember that the optimal KVP. Remember the optimal energy is 35, right, for an iodine angio study, and a little bit higher than the 33. Well, let's plug it into our little equations. Remember that E effective in the middle of a patient is 1/2 of Emax, right? It's 1/3 of Emax at the surface, 1/2 of Emax in the middle of the patient. So that 1/2 Emax equals 35, the desired energy. Well, solving for Emax, it's 70 keV, but remember, the Emax is equal to the KVP. So to get 70 keV, you set 70 kVp. So that's the answer. The ideal voltage would be about 70 kVp. That's where you match that K edge with the predominant number of photons in the X-ray beam. Now, if you have a thicker patient, then you need more penetration through that patient. Thus, you have to creep up on the voltage so that larger patients, you may not be able to do 70 kVp. You may have to go up to 75. You may have to go to 80. You're going to lose, the higher the voltage, the more loss you have of the being away from the peak of that K edge. But remember, you're still dealing with atomic number, of iodine, which is greater than the atomic number of tissues. So even for large patients, you'll be able to see the contrast media effect. It just won't be as dramatic. It won't be as good as it is for the thinner patients. Now, for GI studies, we choose barium because barium not only has your additional thickness through the abdomen, giving greater absorption, but there's more absorption of the barium itself in the intestines, and there's more clumping of barium and more concentration of barium. So you need that extra penetration. So the optimal voltage is going to be somewhat higher, more into the 90s, low 80s and 90s. Okay, let's summarize this and move on. We've already seen that you can use the contrast media effect, and it's a K-edge effect, but I want to just expand the horizon a little bit. Look what we have. Iodine is a material that greatly absorbs X-rays. Now, you wanted it to produce subject contrast, but let's think about that. Is there other areas in radiology where you would like enhanced absorption? Yeah, in detectors, when you detect X-rays, you want to be as efficient as possible. You want to absorb as much of the X-rays as possible. So all of our fluoroscopes have cesium iodide. Notice the iodine. Actually, cesium has a K edge in the X-ray spectrum of that we use also. They're very similar, K edges, energies. So you have that enhanced absorption, which means less dose to the patient. You are not allowing X-rays to be lost. You absorb them very efficiently at these K edges. So the digital radiography systems are also based on cesium iodide systems. Okay, so both the classical analog fluoroscopes and the newer digital fluoroscopes, and as well as your digital radiography, they're heavily invested in iodine. Why? Because you want to absorb as much of the X-rays available as possible. So there's an extension of the applications of this K-edge effect. Now, all materials do have a K-edge. How about soft tissue? All materials have a K-edge, but at very low energies, with soft tissue, because of its low atomic number, has a K-edge energy less than 1 keV, number one, so it's way down on the energy scale, but to boot, it's just a little blip. It's not. It's there's not an extraordinary increase. So number one, it's very low energy. So typically those energies don't even get out of the X-ray tube. But even if they were interacting in the patient, there wouldn't be much of an effect. It's a very mild effect. The effect is more prominent at the intermediate atomic numbers and like iodine and barium, etc. Okay, moving on. This is the overall summary of the photoelectric effect. We established that it was the principal determinant of dose. All of the energy involved goes to patient dose. How come? Because all the energy involved goes into characteristic radiation and the photoelectrons that are set in motion. And both of those are relatively non-penetrating, meaning they're all absorbed before they leave the patient. So photoelectric effect is a predominant or the principal determinant of dose. It's the principal determinant of subject contrast. How come? Because of that Z cubed over E cubed rule, which we've been emphasizing all along. And as we just finished discussing, it's the resonant photoelectric effect, which is the basis for the contrast agent effect. And then the last point I made was that you can also use this contrast agent or the K-edge effect for our imaging plates, both in fluoroscopy and in radiography. Let's move on to the next type of interaction that occurs. We're going to go up a little bit more in energy. The last one, the photoelectric effect, as you remember, the energy condition was that you had to be greater than the binding energy. But now for the Compton scatter, notice that I have uh, 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 these these little symbols here. It's very much greater than the binding energy. When you get to very much greater than the binding energy, the electrons are considered to be free. The binding energies of the electrons are so small because your X-ray energies are so high. So relative to the binding energies, those electrons are free. They're and this is what occurs. In comes the X-rays from the coming in from the left on this slide here, interacts with an electron which is now considered to be free, even though it may be bound. But it's the binding energy is so small that it's totally negligible. And remember, soft tissues have a very, very low binding energy. So Comptons are going to be very, very prevalent, very dominant in soft tissues. But what you see here is that you send the electron off in one direction with kinetic energy, and yet the X-ray photon goes off in another direction, and we call that that photon being scattered. When we talk about scatter, we're talking about Compton interactions. There is no scatter in photoelectric effect. If you remember, the photoelectric effect sets in motion electrons. Well, so does this interaction. But then the photoelectric effect also sets in motion characteristic radiation. It does not, the photon that came in photoelectric effect completely disappears. Here, the photon lives on and goes off in another direction, in a scattered direction. And the energy balance would look like this, where whatever energy came in, where did it go? Well, it's split between the kinetic energy of the electron and that scattered photon. And here's an example of that. Given that the X-ray energy is 40, and let's say that the scattered photon is 10, going off in some other arbitrary direction, what is the kinetic energy that's available for the electron? Well, plunking it into that energy balance equation, you can see that 40 equals 10 plus the kinetic energy. Well, the kinetic energy has to be 30 to balance the equation. What happens to that Compton electron? It's absorbed. All electrons, no matter how they're generated, all electrons are non-penetrating. They will be absorbed. They do not leave the patient. They go to patient dose. So notice that this Compton effect does give you a dose a factor, but it's not a total dose absorption because that scattered photon lives on. That scattered photon can leave the patient, and then it forms a problem, a radiation hazard problem for people in the environment. And the reason you wear a lead apron in fluoroscopy is to protect you against scatter generated from within the patient. And the reason we put all of our lead barriers and lead shielding devices is to protect against the Compton scatter. So let's start listing some of the features over here. It's independent of atomic number. Why did we say that? Because the electrons binding energies are very, very small relative to the incident photon. That's the basic condition for this to occur. And but if you say that it's independent of Z, what that really means is it's independent of tissue type, which really means that this is when it happens in the same manner, a likelihood for air as it does for lead. Wow, there's no difference between soft tissues and lead or air and the lead, as long as the incident energy is greater than the binding energy. When we mention lead, it would have to be greater than the binding energy of lead, which is pretty high. In fact, it's very high. But when this occurs, and we're focusing on soft tissues, and soft tissues have a very low atomic number, so that you're not going to be able to make very reasonable images with Compton effects. The images and the contrast comes about because of the photoelectric effect. On the contrary, the Compton effect serves to degrade the images because of scatter. Um, uh, and when this occurs, this Compton effects, it's independent of tissue type, so you cannot distinguish one tissue from another tissue. What good is that for imaging? Not very good at all. You will get an image, but those images are more dependent on density. How many electrons were available to undergo the Compton scatter? Something like a lung, which has a very low physical density, there's not many electrons available, so that a lot of the energy, incident X-ray energy, will go right through and deliver information to the image plate, as compared to the surrounding heart and bone and all the other soft tissues. So you'll see images, but they're more dependent on density rather than on atomic number. It occurs at the higher the voltage, the higher the energy, the more likely you will have Compton scatter, right? So as you go up in kV, you expect more and more scatter, because higher kV implies higher photonic energies, which means that you're going to be even more discrepantly high in energy relative to the binding energies. And there is a variation. It varies as 1 over E. Not as dramatic as 1 over E cubed as we saw for the photoelectric effect. Let's take a look at that in pictures. Here we have the X-ray beam incident on the patient, and scatter is produced. That scatter arrives at the image plate. Remember, we said that it serves to degrade the image. This is the mechanism by which images are degraded. The scatter arrives at the image plate and do not correspond to the tissues that were being imaged with the primary beam. The scatter is just every which way, random arrival of photons generated in the various tissues inside the patient, but they arrive randomly at the image plate. They don't correspond to the actual anatomic positions of the tissues that you want to actually image. And so there's one a downside of scatter. It degrades images. Here's the other downside of scatter. I mentioned that the reason you wear lead aprons in fluoroscopy is because of scatter. That scatter can leave the patient and arrive at you, giving you a dose. Here is a comparison of the Compton effect with the photoelectric effect. Remember, the photoelectric effect goes down very precipitously as 1 over E cubed. Well, that's what I'm showing here in the yellow curve. It's going down very steeply. The Compton's goes down, but it goes down in a more shallow manner. They both go down with energy, but the Comptons compared to the photoelectric effects go up with energy. There's so much more at the higher energies of Comptons that the photoelectrics. Photoelectrics are going down to 0 as you get higher and higher energies. Notice this point of intersection between the two curves. That occurs at 25 keV. We quote that number to indicate at what energy does Compton predominate for soft tissue. Above 25 keV, it predominates, and which now I'm able to answer some very popular questions on the boards. Like, for instance, a patient undergoes chest radiography. What effect predominates inside that patient? Well, now we're able to answer that question. And likewise, here I got a whole list of different scenarios, questions that they've asked on the boards concerning whether you identify whether it's photoelectric effects that are responsible or whether it's Compton effects that are responsible. How about chest radiography? Now, chest radiography typically is done at 120 kVp. And at the patient surface, you get 1/3 of that, so it's 40 keV. Notice that 40 keV is so much greater than 25. So, answer. Compton's predominates even if you're looking at the skin. But if you look in the middle of the patient, where you got 1/2 of Emax, well, then there's even more predominance of the Compton effects because you're so much more greater than the 25. Do you see how we're using that 25 keV as a line in the sand? Anything above it is Compton. Anything below it is photoelectric. How about technetium over in the nuclear medicine area? Now, that's a monochromatic 140 keV, and 140 kV is way higher than the 25. Almost all of the interactions occurring inside the patient after you administer technetium-99m is Compton's. How about thallium? Same thing. And in general, in nuclear medicine, your energies are typically greater than 70 keV, and so that typically it's all dominated. All the interactions inside the patient is Compton's. There's a lot of scatter coming out of the patient in nuclear medicine. How about mammography? Now, mammography is way down in the 20s. Remember that? Well, with molybdenum targets and molybdenum filters, well, that's less than 25. So in mammography, photoelectrics dominate. And this is both true for both molybdenum and rhodium targets for any filter combination. How about bone? Now, bone, the something in my throat here. The number 25 corresponds to a soft tissue. When you're looking at bone, where is the energy at which you have equal amounts of Comptons and photoelectrics? That's closer to 40 kV. Notice that it's higher than the 25 for soft tissue because bone has a higher atomic number. And but notice that being higher in energy, 40 kV, there you have a greater chance of photoelectrics to occur in diagnostic procedures. And most of the time, that is your dominant process in bone. How about in iodine? Now remember, iodine it's all based on photoelectric K-edge effect. So forget about energies. In a contrast study, you're always working with the K-edge effect, which is strictly a photoelectric effect. There is no such thing as a Compton K-edge. It's the photoelectric K-edges. And then in lead, lead is such a high Z that essentially photoelectrics always dominates in lead. Okay, let's look at some of the Compton angle. If there's any questions on the basic interaction, let me know now. And this idea of being able to identify what kind of effect dominates for any particular exam. Okay, moving on to Compton angle relationships. I gave you this when we introduced Comptons, but there's all possible angles involved for the electron and the scattered photon. For instance, what if you came in from the left, shown with the red arrow, and you hit an electron square on, a square-on collision with an electron? Well, the electron is going to be sent directly forward, and the photon is going to go directly back. We call that backscatter. And when you have backscatter, you are imparting maximum energy to that electron. It's very much like a billiard pool interaction, where if the cue ball hits directly square onto a ball on the table, that table goes off with relatively high energies. It goes off in a straight line with maximum energy. The same thing occurs with Comptons. In a backscatter effect, that photon sends that electron straight forward with maximum energy, and the photon goes backwards with a minimum amount of energy. Most of the energy goes into the forward electron, and the minimum to the backscattered photon. Here's the opposite. How about if the X-ray photon comes in, but rather than a full head-on collision, what if it just barely grazes the electron? Just barely tangentially, just barely touches the electron. Think of a billiard pool table interaction again. As a cue ball just barely tangentially touches one of the balls on the table, in what direction does that ball move? It moves perpendicular to the direction of the cue ball. The same thing is going to occur in Comptons. The The electron goes off at 90 degrees, as shown on this bottom of this slide, and it goes with a very low energy, just like happens on the pool table, where that ball that got struck just barely tangentially goes off at 90 degrees, but very slowly. It doesn't have very much kinetic energy. Likewise here, the electron doesn't have very much kinetic energy, while the photon goes straight forward. That's why we call it forward scatter, and it goes off with a maximum of energy. So what we see here are the two extremes, where the electron can either go off with maximum energy or with minimum energy, and likewise vice versa for the photon energies. Summarizing this then, we see that the Compton effect, which works with independent of atomic number at energies very much higher than the binding energy, you will have the interaction independent of tissue type. And if it's independent of tissue type, very poor contrast, very poor delineation or a depiction of differences between tissues. The Compton effect depends more on the electron density. How many electrons are available to be interacted with? Okay. Then, of course, you have that scatter, which further degrades subject contrast and presents a personal hazard. And then I mentioned that 25 keV as that energy above which you will have your Compton predominate. Okay. Okay, that takes care of Compton effects. Notice we did not say nearly as much about that as we did photoelectric effect. Moving on to an even higher energy, energies that exceed 1.02 MeV, we have this interaction which we refer to as pair production. Now, that kind of energy, 1.02 MeV of energy, is so great. Let me check something here. That kind of energy is so great. We don't have those kinds of energies. We never go up to that 1.02 MeV. In nuclear medicine, we go up to 140 keV monochromatic for technetium. In PET scanning, we go up to 0.51 MeV, half an MeV, but there's no modality that goes up to this amount. So why are we looking at it? Because ABR says we should look at it, so we look at it. But don't expect this to occur in any modality in radiology. But what is that process? Here comes the X-rays. But notice now that that X-ray photon is going to interact with a nucleus. Now that makes it different. All the other interactions we talked about were the photon interacting with electrons. Whether they were free or bound, they were interacting with electrons. Now this process interacts with the nucleus, and more specifically, it doesn't have to hit the nucleus. It will occur at in the field, the nuclear field of the nucleus. And when this occurs, something very extraordinary happens. You have that X-ray energy, which is photonic, it's electromagnetic, it's pure energy. But that pure energy, poof, disappears, and what appears are two electrons, two antiparticle electrons, one negative, one positive, going off in different directions with a certain amount of kinetic energy. Here we see pure energy in the form of a photon being converted to pure mass. And what relationship governs that? Yeah, Einstein's E equals mc squared relationship. Remember that? That is telling us that energy and mass are interconvertible. And that's exactly what we're doing. We're converting energy to mass. And it follows this generic equation, where we see, if you remember, is the speed of light, m is the mass, and E is the relativistic energy. And if we put in the mass of electron into this equation and multiply by the speed of light squared, which is a huge number, you come down to that one electron is 0.51 MeV. That's the energy equivalent of one electron, but you're producing 2 electrons. So that's where that threshold energy, 1.02 MeV, comes in. You got to have and exceed that threshold to have this pair production process kick in. So we have the photon interacting with the nuclear field. We have that it has to exceed that threshold energy of 1.02, given from that E equals mc squared relationship. And and we saw that you have to have that 1.02 threshold. The photon coming in is completely absorbed. All of the energy goes into the process, and all of the energy goes out in the form of 2 electrons, kinetic energies. Okay, we've already mentioned that this does not occur in the diagnostic range of energies because we have pretty much of a cap at 140 keV. And for X-ray energies, in CT scanning, some of our energies now go up to 140 keV, corresponding to 140 kVp. In nukes, we had already mentioned TEC, which is at 140. PET goes up to 0.51, but we don't, as we just mentioned, we just does not occur in the DX region. How about the energy balance equation? Let me remind you, you should be able to walk into the boards with a minimum of under what conditions do the various processes work, number one, and number two, once the interaction occurs, what happens to the energies? What is the conservation balance energy equations? For pair production, here it is. Whatever X-ray energy you're coming in with, number one, you have to invest 1.02 MeV of energy. It won't happen without you contributing that energy to convert pure energy to pure mass. Once you have the electrons, then the electrons take off with the remaining amount of energy. That's your energy balance. Now, unlike the other interactions, we have to make a big deal about the charge balance, conservation of charge. Whatever charge comes in has to be maintained, has to be conserved. So the total amount of charge in has to equal the total amount of charge out. And the photon comes in neutral, right? It's just as often negative as it is positive. But then you produce 2 electrons, and guess what? They have opposite charges, so they add up to neutrality. So neutral in, neutral out. No new charge is created. Okay? And let's take an example and see how the numbers work out. Let's say that the X-ray energy was 3 MeV, 3.02 MeV. What is the kinetic energy of those electrons that are set in motion? Well, plunking in 3.02 into the equation, incident X-ray energy in, a 1.02 invested, you can see that the kinetic energy has to be 2 MeV. Now, those would be split between the 2 electrons, so they don't have to necessarily be an equal partition of that energy, but you can see that you get on the average about 1 MeV each for those electrons. And what happens to those electrons? What happens to their energy? All electrons, regardless of how they're produced, all energies go into patient dose. So they're completely absorbed, and it's absorbed within millimeters. Even though they may have relatively high energies, electrons are just not very penetrating. They all go into patient dose. How does this vary? What determines the how frequent this interaction occurs? As far as I know, they've never asked for this relationship on any board exam. It goes directly proportional with atomic number and directly proportional with energy. Okay, as long as you exceed that threshold energy. So it's almost linear with atomic number and energy, so that The frequency goes up as your Z goes up, as your energy goes up. Now, if we focus on soft tissues, even if you had those very high energies incident on soft tissues have a very low atomic number. So even if you were up in the required energy range, this would not occur very often in soft tissues. It'd be very negligible in soft tissues because of the low Z of the soft tissues. You got to be very high Z's as well as very high energies. Now, we've produced those electrons. What happens? What's the eventual fate of those electrons? Let's let's first of all look at the negative electron. The negative electron is just like any other negative electron that you set in motion. Eventually, they'll be absorbed, and eventually they'll fall back into some orbit, and nothing new there. What is interesting is what happens to the positive electron, the positron. That positron, that antiparticle, is a very strange particle, but regardless of the fact that it has a positive charge, as it zips by various atoms and molecules, it will transfer energy without directly interacting with these molecules. It'll transfer energy, and sure enough, it will lose energy toward the end of its track. It will straggle. Remember, we mentioned that earlier. All charged particles at low energies at the end of the track will straggle, will meander, will have an erratic path, but regardless of that, they lose energy. At one point, when the electron, that positron, has lost most of its energy, it will be attracted to and combine with a negative electron. As long as it has a very high energy, that positron will just zip right through all these molecules and won't interact directly. They'll just interact indirectly with the various molecules. But eventually, as it comes down to kinetic energy 0, it will combine with a negative electron, and poof, it will disappear. And you'll have two photons that are going to appear, they're going to be produced. Notice I've drawn them at 180 degrees to each other. What's going to happen is that upon annihilation, we call that process annihilation, where these two electrons of opposite charges neutralize and destroy each other, annihilate each other. Now you have pure mass going back to pure energy. The pure energy in the form of two photons, which we call annihilation radiation or annihilation photons. Two photons produced at 180 degrees to each other. Sometimes we call that collinear production of annihilation radiation, given by E sub A and N, annihilation radiation. Okay, so we have this process of pure mass going back to pure energy. Hey, at the back end of the pair production process, you have the opposite effect. Up in the front end, you had pure energy going to pure mass. Now you got the opposite. You have pure mass going back to photonic, pure electromagnetic energy. But now that photonic energy is at opposite directions, and they have a particular energy, 0.51 MeV. Sound familiar, that number? 0.51 MeV. Where did that come from? Well, remember that you have disappeared two electrons. You have to take into account what happened to that mass. Einstein equation says it's converted to energy, but it's converted by E equals mc squared. So we've already seen that the energy equivalent of an electron is 0.51. So if you destroy that one electron, you got to get 0.51 back out. And in this case, you destroyed two electrons, you got to get two of them out, 0.51 MeV each. Annihilation radiation always has 0.51 MeV energy, always. One of the trick questions that they've asked on the boards is very simple sounding question. It says, what is the energy of annihilation radiation? And then they give you choices. And one of the choices is 1.02 MeV, and a lot of residents go to 1.02 MeV. They remember that 1.02 MeV. It is not 1.02 MeV. It is 0.51. 1.02 is the sum of those two 0.51 electron photons. Okay, so the correct choice for that question, what is the energy, annihilation radiation energy? It's 0.51 MeV. You just have two of those. But now we have to consider another law of conservation, a conservation law. We've looked at conservation of energy. We've looked at conservation of mass. Now we have to consider conservation of momentum, And whenever you have a particle moving, a particle with mass that's moving, we say it has momentum. And at the point of annihilation, if that positron had any residual momentum and then the positron disappears, what happens to the momentum? It has to be accounted for. So we have to consider that. Now, one point that we should also mention before I show you what happens to the momentum is that remember the energy that you invested up front was 1.02. Just want to emphasize on this slide that you get 1.02 back. So there's that completion of the conservation of energy. You invested the 1.2 up front, and it just doesn't go into nothingness. It comes back at you at the back end in the form of that annihilation radiation. So we've seen that you have conservation of energy, you have conservation of charge. Now we're going to have to talk about conservation of momentum, okay? And normally these photons, annihilation photons, are emitted at 180 degrees. But what happens if there's still some residual momentum for that positron? And what will happen is that if that positron has any residual energy, energy greater than zero, that momentum, that energy has to appear somewhere. It appears in the form of less than 180 degrees. You don't always have collinear production of annihilation radiation. You have something that looks like this, where normally you would expect that straight line given by that dashed line, that would be collinear production. But if there's that momentum that has to be conserved, then the annihilation radiation goes off with some finite angle, so a finite forward angle, something less overall than 180 degrees. Okay, this turns out to be crucial in PET scanning. In PET scanning, we always assume the algorithm always assumes 180 degrees collinear production, and they're all the algorithms, all of the in PET scanning is based on 180 degrees. Well, what happens if you don't have 180 degrees? Like in this process, this occurs more often than we'd like to admit, more often than not. So this has to be taken into account in PET scanning. Next time, I'll go to my whiteboard and I'll illustrate that for you. Just one more point before we leave this, and that is I've been looking at pair production. There is something called triplet production, where you have 3 electrons set in motion. Let's take a look at that. Again, the incident photon interacts with the field of a charged entity. In pair production, it interacts with a charged nucleus, right? Positively charged nucleus. But this can occur in any electric field, it turns out. It's much more probable with high atomic number masses like a nucleus It's relatively improbable with an electron, but it does happen. So let's talk a little bit about it. The photon interacts in the field of the electron. It kicks the electron in one direction. That's the one that goes up, let's say. But then you have the production, the regular pair production of a negative electron and a positron. So count them. Now you have 3 electrons set in motion. The two from the pair production, and then the electron that gets kicked. The electron, since it has such little mass, will get a recoil, and as compared to a nucleus that has a lot more mass, so that it just absorbs any recoil energy. So here, the electron just recoils, and you have those 3 electrons. So looking at the bottom of the slide, the photon coming in, interacts with the field of a normal negative electron. Again, you have the 2 electrons and 1 positron being formed. But notice the threshold energy of this, 2.04 MeV. Well, if pair production was not important, interaction, well, triplet is going to be even less important. Just want to introduce you to some of the terminology. By the way, doesn't pair production sound a little bit like PET scanning? That's why I want to go to the whiteboard the next time and show you the difference between PET scanning and talk a little bit about PET scanning because that's always of great interest these days. Okay, so let's put the whole thing together, and we're pretty much finished with the interactions. You remember at very low energies, you had coherent scatter. At the very lowest energies, and then you graduated to photoelectric at somewhat higher photon energies, and then on to Compton effects when you had even greater photon energies, but they all were involved either orbital or free electrons. Then we went on to pair production, which involved the incident photon interacting with the nucleus. We saw that in the diagnostic range, the Comptons generally predominate. The exception to that is mammography, which had very low energies, and contrast media that depends on the K-edge effect, which is purely a photoelectric effect. A photoelectric effect was a total absorption effect, going all the energy available goes into patient dose, and it was also the prime determinant of subject contrast. And finally, Comptons produced the image quality degradation. I got a number of summary tables over here of the energy condition for each of the interactions. And the energy balance for each of the interactions. Do sit down and look at these. I've been having some trouble with the recordings getting them to you, but they will get to you eventually, even if I have to mail them to you. Then you have your the atomic number and energy relationships. Remember, Z cubed over E cubed, 1 over E for Compton and ZE for pair. Then importance, what does it do for us? What is important in imaging? I won't go over all these, but the table will be there available for you to look at. Okay, enough said for the interactions. Now what we want to do is look at the actual quantitation of those interactions. We always like to put a number on things, right? For instance, here's an important number for you. You're going to put on a lead apron for fluoroscopy. How much does that protect you? Of all the radiation that's incident on your lead apron, how much gets through and hits you? Now, that's a number you'd like to know, isn't it? That number, by the way, is 2%. 2%, a typical lead apron will allow around 2% of the incident radiation through the lead apron and giving you a dose. Okay, so we want to get numbers on this. So we're going to be looking at more quantitative relationships over here. I already gave you the example of the lead apron, but how about radiation through the walls? You may have an office on the other side of a facility, X-ray facility. How much gets through the walls? You're about to inject some radioactive material into a patient over in the nuclear medicine area, you're going to do it with a syringe holder. How much gets through the syringe holder? And on it goes. We're going to be using these attenuation coefficients. We're going to be using the attenuation law. So in the little bit of time that's left, let's start looking at that. We're going to be this attenuation coefficient. An attenuation coefficient is going to be a measure of the probability of, for instance, photoelectric effects or Compton effects or pair production effects. We've looked at each of these effects individually, but now the question is, how do we put numbers on them? We made very qualitative statements like, oh, Compton's predominates in CT scanning or in nuclear medicine. But how much more does it, give me a number. This is where we're going. And we're going to express those numbers with this idea of an attenuation coefficient, which is going to express the probability of an interaction occurring, of an attenuation event occurring. The unit of this coefficient is going to be per unit length, reciprocal length. Mathematically 1 over millimeters or millimeters minus 1. We rarely talk about centimeters. We typically talk about millimeters. And with that attenuation coefficient, we can do quantitative calculations and come up with numbers. Okay. Remember these three interactions? Let's put them all together on a plot. Before, I was plotting the probability of the event, but now I'm going to plot mu, which is going to be a measure of the probability of the event. And as before, we have the photoelectrics at low energies. We have the Comptons in the intermediate energies, crisscrossing photoelectric at 25 keV. And then the photoelectrics progress down to very close to zero at very high energies, while the Comptons continues and intersects the pair production. But the pair production, remember, had that threshold energy of 1.02. So we've looked at these kinds of curves before, but now I am plotting them in terms of attenuation coefficient, which is going to be an index of the probability of these various interactions. Now, notice that if you have these three interactions occurring simultaneously, then we can get the total at any one energy, right? And I've drawn in with red the total. Notice that at very low energies, photoelectrics dominates the total, all right? And in the intermediate energies, the Comptons dominate, and at the very high energies, the pair production predominate. But the overall curve is going to be looking like I've drawn here, where very low energies is steeply falling down with energy, then sort of, it doesn't quite flatten out, but it doesn't. It does go down with energy, but not nearly as quickly, and it's roughly linear in that region, as we mentioned before. Okay. Here is the attenuation coefficient. If I were to break it down by individual components, there's a coherent component, and I add to it the photoelectric component and the Compton component. Those are the two important ones. We saw that the pair production is really never really applicable for us, and the coherent scatter occurs so infrequently that doesn't add very much in, but it is one of the components that appears or contributes to this total attenuation coefficient. From now on, we're just going to be calling it attenuation coefficient. Assume we mean total. On the boards, when they say attenuation coefficient, unless they're very specific and they've never really broken it down by components, assume that they're talking about the total. Okay. There's other coefficients that we, the only other one that may be mentioned on boards is the mass attenuation coefficient. These other coefficients, if they are mentioned, they're mentioned as something that doesn't apply to the question. There, you know that every question they got A, B, C, D, and none of the above kind of thing, and they always give you one component that really is has nothing to do with the question. But of course, if you don't recognize it doesn't have to do with the question, and you're in the guessing mode, you could be guessing the wrong question, the wrong answer. So I'm giving you these more for the the terminology. The mass attenuation coefficient has been mentioned almost just as often as a straight attenuation coefficient. I noticed our time is up, but let me just define the mass attenuation coefficient, then we'll call it a day. Here's the definition down here. It's the, and we'll pick this up at the next time, but if you just divide by the density, the physical density, grams per cubic centimeter, if you divide the mu by the density, that'll be your mass attenuation coefficient. It takes into account the density of the material. Well, let's stop there. We'll talk more about these awkward looking units and what this mass attenuation coefficient really tells us. But at that point, if there's any, open it to any question, otherwise we'll let you take off here. Okay, if you, I bid you all a good day and we'll catch up with you later. Have a good one. Bye-bye.